Hello and welcome everyone. I'm your host Stefan Burns, geologist, geophysicist, space weather guy, here with an update for you as to the volcanic state of the globe. And just in general, basically a geologic update for everyone as to what's happening on our planet. We're really in unprecedented times as it relates to our planet, as it relates to our ability to track changes with our planet. 800 years ago, there's all these events that were occurring that we basically have no record of, though the very big ones we do. Now we have seismographs everywhere, we have satellites in space, we have people probing into volcanoes, measuring the magma, the gas composition, the mineral composition. Wonderful, amazing, hardworking geoscientists all across the world, data scientists and more, giving us an unprecedented level of, I don't want to say understanding, but detail as to what's happening. And understanding is hopefully the cohesive picture that emerges from studying this, integrating it, and seeing the bigger picture, which is what we do here on the channel. So if you want to stay up to date on everything that's happening with the Earth, energetically, so that's earthquakes, volcanoes, severe weather, geomagnetic storming, from space weather, solar activity, planetary alignments and resonances, interstellar, cosmic forces, consciousness, everything and more, we cover it here on the channel. But there are some pretty big changes unfolding. There's some evidence that we are going to be going into an even more heightened state of volcanic activity in the years ahead. That's not a guarantee. I think it'd be very egotistical to think that just one person knows exactly what's going to happen to the Earth. The Earth is a much more complex system than one brain can, understand, even if they've done a lot of studying or whatever. So there's a huge unpredictable element to this, but we can issue some general forecasts based on the best knowledge and understanding that we have. But keep that in mind. Fundamentally, we could be in for surprises in either direction. But we do see trends across time, and we do have evidence of things happening right now that are quite significant and indicating that we probably have more coming. So what we're looking at right here is some really incredible footage from Kilauea volcano on the big island of Hawaii, Hawaii's most active volcano, though it is not the largest. This is episode 49. I thought it was fitting to open with this because we see two of the main systems right now that are really active and dominant, almost like the two elements. We're having huge changes to our atmospheric system. I mean, right now we have a super El Nino rolling through. That changes the hydrosphere and where water is on the planet. You have a huge upwelling of warm water off the coast of South America. You have changes to the hurricane season in the Caribbean and in the Atlantic. All across the world, you get big changes with La Nina and El Nino cycles. And with the super El Nino, they're quite severe. And historically, you look at El Ninos, like the super ones, the Godzilla ones, and they've brought about crop failures and famines, and it can be very, very serious. So, but here at Kilauea, we have this lava fountain that's about 600 feet tall. It's the 49th eruptive episode for this volcano since December of 2024. So it's about a year and a half. The prior record for a lava fountain, based off of the historic records that we do have for Kilauea, which keep in mind, this is like a few hundred years, okay? It's not 20,000 or 100,000 years. We would, the big island's like basically 600,000 to 1 million years old. I could be off a little bit on those dates, but in general, it's like in that less than a million zone. So we don't have like the super long record, but we do have records going back to the 1800s and even earlier, and 47 eruptive episodes is what the Pu'u'o'o eruptive cycle from 83 to 86 gave us in 3 years' time. And that was basically a record, and that Pu'u'o'o eruptive cycle actually lasted from 1983 to 2018. And it ended with a strong magnitude 6.9 earthquake that struck Leilani Estates, Kilauea, the south flank, everything. There was a rift eruption there. 700, I think it's like 700 homes destroyed. Big deal. Very big deal. Well, we've had 49 fountaining episodes now from Kilauea in half the time. So this is a record. We've had these fountains go up to about 1,700, 1,800 feet, so like 500 plus meters. This time though, right here, episode 49, they're only 600 feet tall or so. But incredible to see this balancing of the elements. So not only are we seeing big atmospheric changes, and we know that the atmosphere is able to influence the actual spin of the Earth on its axis because of the transfer of angular momentum, which is fascinating. And then if the Earth is spinning and wobbling a little different, you think that's probably going to affect plate tectonics a smidge, right? We also are seeing incredible volcanic activity all around the globe. This is almost, Mother Earth directly giving us a sign of what's happening and what's to come. But there's been a lot more than just, record eruptions at Kilauea. We've been having some volcanoes which have been dormant for 500 plus years erupt. I mean, Krishenikov volcano in Kamchatka was dormant for 600 years. It erupted just last year after a megaquake struck the region. We had Haile Gubi in Ethiopia awaken for the first time in the historic record. This is the Afar region. We think it's probably like the first big eruption there in 10,000 years. So we had Hunga in 2022. So we've had some big changes. So we're going to go through all that today. Just kind of basically like a review of a lot of the different things. Because if you just learn one story, like the mainstream media, God bless them, they don't cover a lot of these events. And so if you hear of just one of them, then you're like, oh, okay, that's cool. Or, oh, wow, that's interesting, right? But then that's it. You don't get the full sense of what's unfolding here on this planet. And there's always changes and new things and that, whatever. But when you start to just look, okay, oh, like that too? Oh, you start to really get a sense of, okay, like this, there's a clear trend, progression, and even story, I would say, with some of these changes that we've been tracking. So hello and welcome. I'm your host, Stefan Burns. Let's jump right in. And we're going to be all over the place here, but we'll start with Google Earth. And we're going to start with earthquake activity because we see that the Earth has an influence in terms of earthquakes over volcanic activity. And a new research paper just came out of Japan that very clearly, well, it's not out of Japan, but for Japan, that very clearly illustrates that. There we go. So here's Japan. It's been very active over the past about 8 months now. We've had multiple magnitude 7s, multiple magnitude 6s, tons of 5s and more that have struck Japan over the past 8 months. We've also, of course, had a magnitude 8.8 megaquake that struck end of July 2025. Right in this region, we just had an aftershock there, a magnitude 6.6. A minute before this one, we had a magnitude 6 pop off. And of course, you'll remember the fact that we had a big earthquake strike the Philippines recently on the 7th of June. I think it was the 8th for them, local time. And that was very significant. We see the seismic waves propagating for that right here across the globe. When you get a big earthquake like this, high magnitude 7, magnitude 8, magnitude 9. If magnitude 10, the voice would have to go even deeper, magnitude 10. Then you get these surface waves to travel all across the globe, and not just once. This is the antipode. They'll culminate again at the antipode. They'll then even keep going once more. I guess I need to put this on repeat. 1 second. I don't know why that one's not looped. Here we go, though. So these continue to radiate out, but they don't just radiate out across the globe, they also radiate through the interior of our planet. And the volcanic activity that we've been seeing is in many ways indicative. It's like telling us and giving us a clue as to these internal dynamics and properties. So here we see ray paths going through the Earth. So you have some sort of earthquake, okay? We'll call that right there. And you get these different seismic waves that propagate through. You have P waves, you have S waves. Surface waves, of course, travel on the surface. So about 70% of the energy in an earthquake is propagating through the crust along the surface. But you do have these compressional waves, which are traveling through the Earth. They can travel through the mantle and the inner and outer core. And you also have shear waves. Now, I suppose I should pull this up for you really quick. Let me show you the difference of what these look like, because I do have a nice video here showing you wave motion. So anyone that's kind of just jumping in for the first time, this will be useful to see here. But we see P waves, they're a nice compressional wave, just like that. So it's the actual particles kind of oscillating like this, allowing that wave to translate through. You only have one type of P wave, okay? Now next up you have shear waves, where you get this shearing motion like this. So you can have vertical shear waves, and that creates vertical displacement of the ground at the surface, or you can get horizontal shear waves like this. Those are typically more destructive as it relates to buildings, collapsing, things of that nature. But here, I think it only shows vertical shear waves. Then you'll also see surface waves after this, and we'll see horizontal surface waves called love waves. And then there's also Rayleigh waves, which are vertical surface waves, and those are very destructive. You typically get stronger Rayleigh waves than love waves, but you can have both of them. So these are what seismic waves look like at the surface, okay? Well, we also get these traveling through the Earth. And so you have refraction and also reflection. Reflection is where a wave will go down and bounce right back. Refraction is where it'll hit a different rock layer and refract at some angle. So we see that clearly right here. It's going like this wave there. This is a P wave, refracting now at the inner core, traveling through. The K stands for core, and then refracting back again to show up on the other side. So PKP means P wave traveling through the core and then emerging again as a P wave on the other side. Here, for example, we see a P wave refracting through shallower, and then here it refracts again as a P wave and then refracts again as a P wave. Here we see this P wave refracting and then refracts as a shear wave. So they can kind of translate and move around in terms of their characteristics. But in general, a strong earthquake, like I just showed you with this magnitude 7.8, it can, not only send these waves all around the globe multiple times. The Earth is ringing for hours, right? Look at the time here. This is 40 minutes. It's going up to an hour, right? There's some people have talked about how moonquakes, the moon rings like a bell, and that's true. These moonquakes that we've observed, the moon will ring for like an hour or so. And that's just a metaphor description. Basically, there's not that much attenuation for the moon, so the seismic waves can continue to propagate for a while. The Earth does the same thing, but we get much bigger earthquakes than the moon, which is why even though there's more attenuation with the Earth, these waves getting absorbed into other parts of the Earth, that's your first clue as to how earthquakes and volcanoes connect. We can have this last for quite a long time, as you can see. So going back to our ray paths, but you also get them not only along the surface, but on the other side. And you have a shadow zone for P waves because of the angle of refraction, and shear waves don't go through the outer core because it's liquid. That's kind of crazy. Below our feet, there's a giant pool of liquid. Like, that's kind of wild. We think the same is for the moon. We think that there's a fluid core component to the moon. Kind of wild. And it has to be liquid. It's not like it's a super, like it's fundamentally liquid because these shear waves don't propagate through liquids. But P waves they can emerge on the other side. So we have these waves propagating through the entire globe. Now, what was just recently found? And we'll go to this article here. This is really, really cool. So what was just recently found is that for the 2011 Great Tohoku earthquake in March, the magnitude 9.1, the big one, we had, where's the GNSS? I'm looking for a graphic here. Okay, there it is. So for the big one, they of course measured slip on the fault. When you get a big earthquake, you're getting movement on the fault and the plates, and you can get, for example, lateral movement for, let's say the San Francisco earthquake 1906. You can actually, the plates are moving past each other. You can get a displacement of 3, 4, 5 meters. Some places it'll be, I think the average was like 3 meters for the Great SF quake. And then the maximum was like 5 meters, something like that. So, huge moves. There's photos from San Francisco, the Great Earthquake, where there was a fence, like in Marin County, and all of a sudden afterwards the fence is shifted off by like 10, 12, 15 feet. So it's like really significant. And we can actually see that very clearly here. If we watch this video, okay? This is from the magnitude 7.7 last year. You will literally see the ground on the other side move. Watch here, the fault is right here. Watch how it shifts. It's like this, right? There, boom, you see the cracks form. Oh, what? This is the first time we've ever seen a fault movement like this on camera so clearly. Big earthquake. This is magnitude 7.7. Magnitude 9.1 is a lot bigger, all right? Like much bigger, probably like 50 times bigger. Could be more than that. We could do the calculation, but it's fine for this point right there. But again, here we see this, the shaking begins, and then once the fault loosens up, boom, you get that big shift. So that is literally what's happening when we're seeing this stuff, which is crazy. So what they measured is that about 18 minutes after the earthquake, and the shaking by that point from the main quake is done. You have aftershocks, all the other stuff. The main slip from the magnitude 9.1 is over at that point. They measured that a shear wave, the shear waves from this, traveled down to the outer core and reflected back up, and that moved the entire island to the east by about 6 to 8 millimeters. So really incredible stuff. 16 minutes after the earthquake, but before the aftershocks hit, Japan's GPS stations registered an eastward lurch across the entire country, but unconnected to any specific quake or aftershock. Of course, it's connected to the main quake, just not immediately in time. There's this delay. So analysis showed that the shear waves, some of them that were generated, bounced from the outer core back up, causing this displacement eastward by about 6 millimeters. And they've, we've been tracking on this channel, and other people have been tracking this too, about how earthquake activity can sometimes set off volcanic activity or set off earthquakes in other locations. For some reason, there's a little bit of resistance with that idea in some circles, but I mean, it's pretty much like being proven solid. So I don't get the resistance. And just while we got it, big super thanks here from Matty Tempo. Thanks for the gifting the memberships. He is also doing his best to track these changes and everything and more. He has an X account. I don't know about YouTube. I know he's posting about earthquake updates and stuff on X. So give him a follow if you like. But thank you for that super thanks, brother. So seismologists knew that these large waves from earthquakes travel through the earth, can even reverberate off the core, but this is the first time that we saw a very clear slip on a plate associated with one of these reverberated waves. Now, shear wave, again, it's not going to travel through the outer core because it's liquid, so this is a reflection off the inner core. Well, it's traveling the Earth's radius is 7,000, and no, it's like 6,700 kilometers, something like that. Maybe it's 7,600, whatever. The mantle is pretty thick. It's like 3,000 kilometers thick, probably more on the 3,000 side. So that's traveling a good distance. Takes some time to travel through that. And think of all the attenuation that happens. So much energy is absorbed by the mantle as it travels through, and then also back up. Even then, there's still enough energy the journey back and up about 5,800 kilometers took 15 minutes. Even then, now that the fault was loosened, Japan was able to move off to the east. We can see that with this graphic here from the supplementary material from the study. And we see the motions of the plates here. So this is the Philippine Sea plate right here. This is the Pacific plate. It's going 80 millimeters per year that way. This is going 63 millimeters per year. After that main quake, 16 minutes afterwards, a lurch. There's actually multiple lurches that accumulated with about that 6 millimeters of displacement, but we see the arrows on that right here. So there's the entire island Japan. Now, interesting thing about Japan, if you go to Google Earth here, is that we see that they've split Japan in two. You have the Sea of Okhotsk plate right here, and then you have the Philippines Sea plate right there. But if you look at it, it's kind of a white here indicates like a kind of an unusual plate boundary. So really, you look at this. This is one continuous segment going all the way down. Let me get this better positioned right here. This is really continuous going all the way down to the Philippines like this. So yeah, they do have this unusual plate divide there, but really almost it looks more contiguous for a plate, the Sea of Okhotsk plate right here, and then this would almost, this is different. Then the Philippine Sea plate takes up over there. But they must have some earthquake activity that indicates a plate boundary right there to some degree, right? But this entire landmass shifted to the east, which makes sense because this is a reverse thrust fault, shallow. So basically you had Japan pushing up over like this over the Pacific plate, which is subducting here, not only under the Eurasian plate, but also under the Philippine Sea plate. So you actually have double subduction occurring right here. Like right here, for example, you have it subducting, and then you have the Philippine Sea plate subducting. So think of like a layer cake, both of them kind of going down fundamentally in this area. So they measured this actual movement. So this shows that these powerful earthquakes, right, the magnitude 9.1 or the 7.8 Philippines, or we saw the fault movement with the 7.7 in Myanmar, Burma last year. That was March 28th, 2025. Kanchaka had a big movement with the megaquake, magnitude 8.8, one of the largest ever on record. We see how these waves are powerful enough to really move the Earth around. Well, if that's the case, imagine that force passing through magma chambers close to the surface. Or how is that perturbing the fluid upper mantle, which is molten in magma? It's not that crystallized. The crust is crystallized, right? Earth's crust is crystallized, especially as you get close to the surface. But the mantle, it's like a solid technically. It has some viscosity to it. But in general, it's pretty solid. Think of like a really thick taffy or something. But there are parts where if you can get melting to occur, like through decompression, like what happens with the subduction zone, so as it goes down, water, what we think, water comes out of the plate that's subducting, causes this decompression melting, and this is why you have big volcanoes across Japan. Like you can look and you'll find these big volcanoes all over the place, right? Here's a big one right there. So, and then you have some real monsters off the coast. Kakai volcano right there, 7,300 years ago, gigantic eruption. They can go off at any time. So the mantle is just one step away from basically going molten in magma. And that then now is a little bit more fluid and susceptible to, I would say, external forcing. Okay, well, what's been happening recently? Well, we've been seeing a ton of activity. So let's just go through what we've been seeing for the past few weeks here. We've had a sequence of earthquakes, this 7.8 being the biggest down here, 6.5 being the aftershock. Then we had Indonesia, Sulawesi on the 16th, 6.7. That was an extensional earthquake. So you have the plates kind of moving apart from each other, at least that fault moving apart from each other. Here is reverse quake, just like you would expect, right? This one here traveling that direction over that subduction zone and that subducting plate, the Philippine Sea plate. We also had a pretty big earthquake here in China, 6.3. This is a strike slip with a little bit of that thrusting motion, reverse thrust. And then just recently we had this 6.6 and a 6.0 that struck a day before, or a minute before. Interesting thing to note is that this 6.6 here and the magnitude 6, and there's two magnitude 5.8 aftershocks, and there's been other aftershocks. The moment this occurred, the earthquake swarming we were having here in the Philippines stopped. We had dozens of magnitude 5 plus earthquakes as aftershocks after that 7.8. You would think that it would just kind of keep going because it's its own thing. Well, and it was just nonstop, providing the majority of earthquake activity for the globe over the past, well, since that occurred, so over the past couple weeks, a little bit less than that. The moment this popped off, the swarm activity here, magnitude 5 plus, totally quieted down. Now look here, they're about equidistant to Japan. So interesting, like, is that a coincidence? I mean, I don't think so. It literally, like, the moment this popped off, the swarm here stopped. So there's these dynamics at play that we still don't fully understand that connect distant parts of the globe to each other. I mean, we know that the plates are connected. They're these, solid contiguous units, and they're going to be flexing, and some parts can deform. Let's say here can deform, and this area hasn't slipped yet. But in general, like, they're a solid contiguous unit. But we saw with the magnitude 9.1 how this entire 1,800 kilometer long zone shifted to the east because of one of these shear wave refractions. So when there's activity happening here, it's also influencing all the other parts of the globe, or up here with the megaquake, all the other parts of the globe. Well, 2025 was one of the biggest years ever for seismic activity for our historic record, which with good data goes back to 1900, but really super high quality data, 1980. That's like seismographs everywhere across the globe. But certainly one of the biggest years since the year 1900. The only years that were bigger than it were the years with magnitude 9 plus earthquakes. So, quite a lot. And we have some examples of how big volcanic activity seems to line up after we've had years of big earthquake activity. A good example of that would be Nova Erupta in Alaska erupting in 1912. Let's type that in, Nova Erupta, one of the two. This is the biggest eruption of the 20th century. Here, 1912. Well, we had a huge year for, actually 3 huge years of earthquake activity, 1905 to 1907. So it's not, a year afterwards or months afterwards, it's a few years afterwards, but you do get this gigantic eruption, which is about 21 cubic kilometers of dry rock equivalent material, a VEI-6 eruption, the largest of the 20th century in 1912, just a few years after this huge seismic burst that came in 1905, 1906, 1907, but 1906 really being the key year. Hungatonga erupted, and let's type that in. We'll get Hungatonga up here. Hungatonga erupted in 2022. Well, that comes just about, 10 years, 11 years after, a little less than 12 years after, a little less than 11 years after the magnitude 9.1 in Japan. And there was tons of magnitude 8s also that occurred in the 2010s. But basically, it's kind of quieted down starting 2022, and then we didn't have any magnitude 8 earthquakes from 2022 to 2025. It was really specifically August of 2021 was our last magnitude 8 quake until the magnitude 8.8 that struck Kamchatka. But Hungatonga having a huge eruption in January of 2022, coming fairly soon afterwards. And then another big eruption Mount Tambora, 1815. This is the biggest of all of these. This is VI6. It created the year without a summer, right? There was devastating 1815. That was about 40 cubic kilometers of material. We can type in Mount Tambora too. Let's see how it pops up. Again, about 40 cubic kilometers of material. There's our big baddie right there. Look at that caldera, folks, right? Still active, though it definitely blew off a chunk. What's the width on this? 7 kilometers. Wow. Yeah, and it's 1,000. It's a kilometer deep at its deepest. That's crazy. So that followed right after 1812. 1812 was a pretty big year for earthquakes. So you see how there's this connection there. We often see, and in the historic record going way further back than just this, that big volcanic eruptions are preceded by earthquake activity at these volcanoes in the months and even years preceding them. So Tambora was a clear example of that. There were earthquakes that starting to rumble. People were starting to kind of freak out. Another good example of that is Hawaii. We were talking about Kilauea. Well, you had a big magnitude, what was it, 7.6, 7.7 earthquake that struck the south flank of Kilauea, 1975. And then shortly afterwards, 1983, you start this new 35-year of eruptive activity. That's the most that's been observed in 200 plus years. That was historic. The Pu'u'o'o eruptive cycle in Kilauea, 83 to 2018, was the most activity that we've seen from that volcano based on the records that we have going back to like the 1800s and even before that. Now we've been seeing more fountaining episodes in about half the time, starting from 2024 December to now. And so you wonder what the heck is happening. You wonder what the heck is happening. We have right now Titan Ridge. I don't know how to pronounce it. Some people are saying it's Teton Ridge, but it's spelled like Titan. You have Titan Ridge, Papua New Guinea. This is a submarine volcanic eruption occurring right in this region that's creating these huge pumice rafts all over. Let's get a photo up for you guys on Titan Ridge because this is pretty crazy. We have some discoloring here. Yeah, this should do it. That's a good photo here of what's happening with Titan Ridge. It's submerged like 500 to 1,000 kilometers below the surface, yet it's still able to, it's creating this superheated steam column that reaches the surface, ash and everything. It's still just pumping like crazy. And we even have a video of it that's really quite wild. Let me get this video up. This was taken by someone on plane on June 4th. So I guess someone was flying over it. And here is the video of this, June 4th, Titan Ridge. Pretty insane, if you ask me. And well, we're presenting on my channel. So look at that. Huge undersea eruption. This is the biggest of 2026. It's still going. And it's creating these huge pumice rafts that are now washing ashore in Papua New Guinea, all the islands. And it's really affecting them because a lot of the people that live in this area, they rely on fishing, and they can't get their boats out, and sea life is dying as a result of the pumice rafts. So it's pretty intense. It's pretty intense. But that's just one example of what's happening right now. But that's a good example because this is, an undersea volcano on the oceanic plate. The plate's not that thick. So you basically have like direct plumbing to the mantle with these sort of quakes, or Hawaii, with Hawaii being a hot spot, right? Direct plumbing to the mantle and even to the core mantle boundary. So these are really good examples of changes to the interior of the Earth manifesting upon the surface. Okay, if we go to Iceland, Iceland had a huge eruption in 2010, as many people know. that grounded air traffic across Europe as the ash cloud moved across. But Iceland is a combination of a hotspot and also a mid-ocean ridge. So you have normal circulation of the mantle coming up in Iceland, so it's rifting apart, but you also have a hotspot there, this normal plume of magma and energy, basically. There's electrical properties to this as well. It's not just like convection, it's also this flow of energy coming up. I think it may be related to a georeactor, georeactor geophysics, which is interesting. But we've been seeing tremendous accumulation of magma based off of earthquake activity here along the smoke spine. We had eruptions, of course, in 2024 as well with Iceland in Grindavik. Blue Lagoon is, I think it's still totally closed down. And Reykjavik is not that far away. Here's Reykjavik, right? It's right near this zone. So there are big changes happening with Iceland. There's a YouTube channel, I think it's called Just Icelandic. This guy tracks this specifically. He's from Iceland. And that's a place to go if you want to stay up to date on Iceland. But what is occurring there right now appears to be really big. It hasn't erupted yet. It's cooled off since Grindavik a little bit, just in terms of surface activity. But there are some Icelandic volcanologists that are looking at what's been happening and saying this could be a new 800-year phase of volcanic unrest in Iceland, because there have been periods in the past that were very, very active. This is I think 800 AD, or it goes quite a way back to when it was originally settled. But if this is some new super cycle for Iceland, then that's a big deal to have Reykjavik right there, because literally any part of Iceland can just start to erupt. There are certain volcanoes, especially under the glaciers, that are well known, Vardabunga and more. But this could be really a civilization event for the Icelandic people if that is the case. Here's a big volcano right there. So you get the idea. There's big changes unfolding in Iceland. We can go over here and let's check out, this is the topic of yesterday's video, Socorro, New Mexico, where there is a giant magma sill that is hidden underneath the surface. We can look at that. Here's a kind of representative graphic for that right here. There is this large horizontal body of magma called the Socorro magma body, about 18 to 20 kilometers down. You have surface deformation occurring about 2 millimeters per year uplift going up. You have earthquakes above the Socorro magma body. So there's an active earthquake swarm and swarming in New Mexico. It's something the majority of seismic activity occurs right over this magma body, yet it only takes up 0.2% of the surface area of New Mexico. So it's very, very active. This almost looks like a juvenile supervolcano. Now, a good example of why that could be the case is Kilauea. Since 2018, we've had tons of earthquake activity under Pahala. And I guess we'll go back to Socorro here. Let's go back to Hawaii. Hawaii is the best studied volcano on the planet. So we learn a lot about just in general volcanism and earth dynamics. And we see this connection between earthquakes and volcanism in Hawaii beautifully. 2018 being a clear example of that. You have the rift eruption start up in Leilani Estates. A day later, magnitude 6.9 strikes, and then it continues on for 3-4 months. Very destructive. But after that died down and the Pu'u'o'o eruption came to an end in 2018, starting around 2019, 2020, you started getting an earthquake swarm here, and this is about 30 to 50 kilometers down, and it's all these earthquakes, since we have so many of them, microquakes and so many seismographs, you can really track them, are creating these horizontal sills. So they're fracturing out horizontally multiple layers, and then magma from depth is coming in and filling them in. And it's also the magma pressure pushing, creating these fractures. So effectively, a new magma storage system has been created under Pahala, about 30-50 kilometers down, that feeds both Mauna Loa and also Kilauea and the entire Kilauea volcanic system. Okay? And I'm sure structures like that have been built before, and then they empty out and maybe they deactivate and they're done, right? Maybe there's a collapse that occurs. But in general, we see that you can have active creation of these chambers. Like, how do you get it in the first place? You know, this at one point was nothing. It was just oceanic crust. It got built up. Things happened to create Mauna Loa. It's a big guy. Well, what we're seeing with Socorro, New Mexico, is perhaps the first sill of many. And the estimated volume on this is already 100 to 1,000 cubic kilometers because it's huge. This thing is massive. It's absolutely massive. So if you were to get multiple of these to form and at different levels, that's a super volcano, baby. This is a mid-crustal magma storage system. Now, a supervolcano like Yellowstone is a full crustal. It has surface expression. You also have Long Valley caldera, right? It's not just mid-crustal. This right now is just mid-crustal. We don't have any active volcano associated with this at the surface, so there's volcanism all across New Mexico. I mean, basically, it's like a volcanic hellscape. Though, and I haven't been to New Mexico. I really want to go visit now because there's some really cool things there, ice caves, and I bet the energy is really incredible there. So, but you know, people that live in New Mexico, they'll be the first to tell you that it's very, very volcanic, has a long history of that. The Vise caldera, supervolcano, it's erupted 1.6, 1.2 million years ago. Huge supervolcano eruptions, 500 cubic kilometers, things of that nature. This is just south of Vise. This could be, you know, the birth of a supervolcano, but it's connected directly into the mantle. So we're seeing an earthquake swarm around New Mexico. That's just one example. Titan Ridge, Iceland, Hawaii. We also had last year, I'm just going through a bunch of examples basically, okay? Last year, remember, January, February 2025, we had a huge earthquake swarm under Santorini. And it was just off the coast. You have the Santorini-Colombo volcanic field. Santorini being well known for its eruption, 1600 BCE approximately, that took this island and blew it apart, right? Colombo volcano, undersea volcano. It had a eruption that generated tsunami, I believe in 1952, but it might be 1954. Either way, 1950s. That generated a tsunami that hit Santorini, and unfortunately some lives were lost with that, I think a few dozen. Well, in 2025, there was a huge earthquake swarm that struck tens of thousands of earthquakes, like, and tons of magnitude 5s, basically nonstop magnitude 5s. You know, when it first happened, a lot of geoscientists came out. The mainstream ones are like, there's nothing to fear as it relates to the volcano. It's not related to the volcano at all. Meanwhile, it's happening right in the volcanic field. So, you know, they were just basically, I think they were A, ignorant, or B, trying to calm people down because the tourist, like, you know, summer season was coming up, which is, anyways, it's a whole thing. Well, the research came out, they really analyzed it once they had all the data, and like, oh yeah, in fact, we had a massive dike intrusion of magma come up. And that's, you know, we have this mid-crustal magma storage system, just like Socorro, right? And we had this huge intrusion of new magma come up, and that is what helped trigger a lot of these earthquakes on these shallow faults. And guess what? You know, those shallow faults are all, they help break the surface apart, weaken it, and if you were to get some huge eruption, well, you know, if you have a heavily fractured subsurface, it's going to allow that to occur. A good example of like just how big a volcanic eruption can be found in the Arctic. Let's just check that out really quick. Now this is not recent, but we see here this giant caldera at the very end of Gaukel Ridge. Here is Gaukel Ridge. This is the northernmost part of the Mid-Atlantic Spreading Center, and let's just actually kind of zoom out so you see that. All across the Atlantic, we have a large spreading ridge, okay? So this is where the mantle's coming up, convecting, new plates being generated and going out like this. Red lines are where they're slipping past each other. Green is where you have that active plate creation. See these ridges there? That's the plate going like this. So you have this, it's like a suture basically. You know, when you're growing, when you're a little kid, or even, it takes some time actually, into your 20s, your head is growing, you have these sutures that look just like this on your skull. And eventually the growth plates close. But they're all wavy and everything, it's pretty wild. Well, this goes all the way up past Iceland. Here's Iceland. Okay, there we go. Look at this. You have another weird depression right there. Like you actually start seeing these all over if you look. This is clearly on some sort of spreading feature. And then you have this big caldera there off the coast of Iceland. You have a big volcano here, Jan Mayen. And if you go further up, Svalbard. You have the Malloy Deep right there. Anomalous drop in the topography, you know, the depth of the ocean. And that's also right next to a volcanic feature as well. Well, you keep going up, the spreading rate really starts to reduce down to about 1 kilometer per year, which is very slow. You have it in the East Pacific Rise at 15 kilometers per, or sorry, not kilometers, what am I thinking? 1 centimeter per year. Gaukel Ridge, 1 centimeter per year at the East Pacific Rise. The Southeast Pacific Rise, it's about 15 centimeters per year. So this is very, very slow. And then right at the end of it, you get this giant caldera. Okay, well, let's measure this. Go across. It's 100 kilometers across. What? 100 kilometers across. If you go back, about 50 kilometers in width. Okay, and it's about 1.2 kilometers deep. So the estimated volume on this is like, I think they estimated at 3,000 cubic kilometers. They associate that with a supervolcano eruption. We've had activity here in 1999 that generated 3 new volcanoes, pyroclastic flows underneath the subsurface. The CO2 concentration in the magma is like 13.5%. Normal, it's like 1.5%. So it's 10 times enriched with CO2, meaning it can be extremely explosive. So we can get these huge, huge, huge eruptions to occur. And it doesn't have to be right on the surface, right? If it's big enough, it can literally explode massive amounts outwards. And you can have, you know, thick crust above it that's a few kilometers thick, and that still isn't enough to contain it. And we see that very clearly with Gaukel right there. So we're seeing these changes all across. Interesting thing to point out with our recent earthquake activity, you know, I mentioned that because there have been some trends. You know, again, Kamchatka 6.6, 6.0, 6.3 China, 7.8 aftershocks as well with Philippines, and then our 6.7 there, Indonesia, Sulawesi. If you plot out the exact antipodes for that, you'll see something quite interesting. If you do that, antipodes, we'll turn on our larger one. This is for the first 3. This is the 6.3 China antipode, the exact opposite side of the globe. And then these 2 are for Indonesia and the Philippines. If we also put our one for Kamchatka here, then you get this. Remember how seismic waves propagate around the globe, right? We'll look at how the antipode region, this is just, you know, each antipode with a line drawn between it, okay? Just showing the general region of the opposite side for those quakes. Look at how it perfectly is centered over the South American plate. That's pretty cool. So it really shows that there are these dynamics. And of course, the South American plate has, you know, is home to the largest earthquake on record, the magnitude 9.5. Right here. There's that magnitude 9.5. So you know that this is a very important part of the globe as it relates to overall dynamics, plate tectonics, and more, because you have the strongest ever recorded earthquake there. But look at how the antipode region is perfectly centered over the South American plate. And if we remove that 6.6 from Kamchatka, we see that the one earthquake that we've had here recently, 6.9, strongest in 18 months or so, it's almost perfectly within this antipode region near the bend, where you're going to get a lot of stress accumulation because of subduction and also the geometry of that kink. So on either side of it, we've had magnitude 6.6 earthquakes strike the spreading centers. Here, Mid-Atlantic, 6.6 right there on the 17th of June. And then also here is our Southeast Pacific rise. We had 6.6 there preceding that 6.9 that occurred near Antofagasta. This is May 20th. So just interesting to kind of see some general patterns here, right? This is just kind of general proof, not 100%, but general proof showing how these seismic energy waves that travel through the Earth affect other sides of the globe. And the Japan data from the 9.1 with that shear wave reflection off the outer core, then shifting Japan by 6 millimeters 18 minutes after the main earthquake, that's really clear proof of that. That's the thing. That's super clear proof of that. So let's go to our, well, let's just quickly just touch on this. You look to the right side of the screen. Here's our 7.8 earthquake right there. We see that we're in a bit of a global seismic burst right now. We had a week after that 7.8 where activity was basically moderate. We had one low day. The other 6 days were moderate. But now we've been in this period of heightened activity after the Philippines. So we're in a seismic burst, 7.8 having more energy in it than all these magnitude 7s over here, but that was a little bit more distributed in terms of the energy going out across time. But we'll go back, and we've also had, just like to kind of add a bit more information to this, we've had Shiviluch volcano really be active in 2026 and also 2025. This is a volcano on the Kamchatka Peninsula, which is where that magnitude 8.8 megaquake occurred. We had 2 eruptions here shoot ash up to the stratosphere, the tropopause, about 10, 11, 12 kilometers up. On the 6th of June, the 7th of June, we also just had one on the, not as high, it went to like 8 kilometers up, but another one just a couple days ago. So we've been seeing tons of activity. Also, Krashenikov volcano was activated for the first time in 600 years after the megaquake. So you see this clear connection. That energy very close by, moving through those magma chambers, activated them. And boom shakalaka, here we go, look at this. Like the Shiviluch is really starting to get active now, because the moment you are able to blast ash, your ash cloud up to the stratosphere, this is a big eruption. We saw a huge eruption as well, similar, with Haley Gooby. This was November 23rd, 2025. First historic eruption from Haley Gooby in the Afar region. This is where you have the African superplume, very, very active. And this, as you can see, a historic eruption. We've never seen this specific volcano erupt in like 10,000 years. We have no record of it. Well, here it is. This was November 23rd, 2025. Huge ash cloud, as you can see. That spread out all the way to Asia and these places I've been talking about, Indonesia, Philippines, and more. Here we see the Afar region. And this is because you have a rift valley going through Africa, rifting the whole thing apart. These lakes very clearly showing that. You often get this connection with water, large faults, and rift valleys. A clear example of that, which we covered in yesterday's video, is you have the Mississippi directly over the Real Foot Rift, which is where the New Madrid faults are. And then also over the Rio Grande is where you have the Rio Grande Rift Valley. Oh, and guess what? That's where this new super volcano, perhaps, Socorro, the Socorro magma body is. It's hosted by that Rift Valley. So where you have faulting and fracturing of the crust, you then get this magma to accumulate, and it can express itself at the surface very clearly, like we saw with Haley Gubia from the Afar region. So this very clearly shows a connection between earthquakes and volcanoes, and we've just been having so much activity that it kind of begs the question of, like, is there going to be some even bigger events coming? Because there can be a delay. It's not instantaneous. Now with Kamchatka and the megaquake, it was almost instantaneous with these volcanoes going off. But I'm talking about the biggest events. But if you have constant activity from different parts of the globe, bing, boom, 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 and these seismic waves are just constantly agitating these magma storage systems, that's going to make them more likely to erupt. So, I mean, we've also, now we need to kind of go back to our earthquake data. Here we have our latest earthquakes, and let's switch this to 30 days. It's not going to cover, well, actually, let's just get everything I want. Let's switch this to the beginning of the year. This should get most of the earthquakes that I want. And minimum magnitude 6, though. Let's search this. And we want this on you. Yeah, it already is. Okay, great. Okay, so, you know, we've had some big activity this year and some deep activity indicating some of these deeper changes. Italy's has had their first magnitude 6 earthquakes in 10 years. First one was here, magnitude 6.0, 375 kilometers down, almost directly beneath Campi Flegrei supervolcano and Vesuvius. So 375 kilometers down, though. This is super deep into the mantle. This is a very deep earthquake. But magnitude 6 there, I was there in Rome for that. I didn't feel it. No one felt it, basically. It's too deep down, and it's only magnitude 6, but that's a big one. And then also 6.2 here in Italy that followed up. That's now the biggest quake, and you see that one's even closer, 243 kilometers, but still very, very deep. So Italy's had 2 big, deep earthquakes that have come in recently. Also, we just had a big super thanks come in from Paul. So maybe Paul III. Thank you so much, bro. Really appreciate your generosity, and thank you for everyone for being here, watching this video, the support of the community in general. So I extend my thanks all to you. If you're jumping in for the first time, you're like, who the heck is this guy? I'm your host, Stefan Burns, geologist, geophysicist, space guy, cosmic bro, here to help you understand what's happening with the Earth energetically. We look at all the different angles. We don't limit ourselves to dogma, but you know, we expand into all the different possibilities. But I do my best to just very clearly label what is, you know, maybe not so proven, speculative, etc. But you know how we came up with relativity, Einstein? It was all thought experiments. You know, he was blasting himself off into space and basically figuring it out. So that's how you actually really figure out what's happening. Is you take the data and then you go one step beyond. All the great thinkers and scientists, that has been their MO. We also see another very deep earthquake here that occurred. Very unusual. Magnitude 7.1. This was on the 22nd of February, 629 kilometers down. And if you look at the earthquake data, and we've done this before, I'm not going to do it this time. I don't want to take this map and refresh it. But if you look at the big earthquake activity for this whole region, it's all clustered around the sides like this. And then this is the one earthquake that's like right in the middle here. And very odd. So what's this? Yeah, so that was like clearly, you know, another indication of these big changes happening in the deep mantle, because at that depth, you don't have a fault. You don't even have a fault anymore. You're in the mantle. There's no faults down there in the traditional sense, unless it, yeah, I can't say anything definitively, but we know very little. These are more akin to implosions than they are like a traditional fault at the surface, rupturing, ground movement, etc. There's a few different ideas as to how they occur. We still are kind of tossing them all up in the air. One of them is that there's a mineralogical change that can happen that is exothermic and releases energy. And there may be a volume change associated with that. So you have like one mineral suddenly transitioning in its crystal structure to then basically create this implosion, reduction in volume, and also you know, expansion of energy. But there's other mechanisms as well. But these are deep focus earthquakes, and that's a very bizarre one. So we saw that occurring, right? Italy, another example. You know, Santorini just nearby. So it's not, and you know, here is the Afar region in Ethiopia. So everywhere you look, we've been having very notable activity. Now, it's not like this has never happened before, but it's all quite significant. It's all quite significant, and it's worthy of mention. You know, there's been a lot of earthquakes over Antarctica. There's tons of earthquakes there. There's a Rift Valley, tons of volcanoes buried under the snow there. So we're seeing these changes unfold across the board. And we have to be mindful of solar activity, because this is one of the big drivers of this, like the big driver of where does the Earth get its energy? It gets it from the sun. 1,360 watts per square meter, baby. It's a lot of energy, okay? The Earth overall, like 170 pentawatts of energy. That's crazy. So this goes somewhere. It's not just completely reflected back. We don't have an albedo zero. This energy affects the Earth in a variety of ways, which we've talked about many times on the channel. You know, the ionosphere gets charged up, electric currents in the surface, electric currents in the ocean, atmospheric circulation. That's a whole separate video. We've done it many times. Here we see the far side of the sun. We do see a big sunspot rotating. I just wanted to mention this while I'm live, but we'll watch this sunspot grow here. And it's just suddenly becoming quite significant. There it is right there. So we do have a big sunspot right now on the far side. That'll be rotating into view in about 4 days or so, 3-4 days. So keep an eye on that. But if we go to our solar cycle progression here, what we observe is that after we have the big increases in solar activity from a solar maximum, that is when we see the volcanic activity respond. There's this inverse correlation. Coffee's good. Okay. So there's this inverse correlation. Look here. Here we have the Dalton minimum in the 1800s, right? Well, remember Mount Tambora, the largest eruption since we haven't had a bigger eruption than Tambora in 1815. Well, we see it occurred right here during weak solar activity. Okay, maybe if I move the cursor up, it goes up. Yeah, it was specifically Tambora. Did I write it down? I didn't write the time down, but it was early in 1815, somewhere in this zone. I think it was like April. Just in general, though, look at the solar activity, quite low. You also see this periodicity here. These are Gleisberg cycles. Now, not everyone's convinced that they exist, but I'm on Team Gleisberg, personally. Here we see another reduction in solar activity at the end, in the beginning, end of the 19th century, beginning of the 20th century. Well, when did Nova Rupta occur? That was 1912, right? Look at Nova Rupta right here during, again, I need to move this cursor for you guys. Right here, during a solar minimum within a Gleisberg cycle. All right? If you go forward, we have our most recent, and not to switch sides, we have our most recent period of low activity, solar cycle 24, really exemplifying this. 25, though, while we did spike up to 215 sunspots for the monthly count, August of 2024, we see that it has not been as strong as solar cycle 23 here. Very clearly has not been as strong. It's still, you know, a weaker solar cycle. Our sunspot numbers right now are hovering around 100. So we're in the descending phase now. But, you know, we had what was it? Hunga Tonga in 2022 pop off, right? Well, where's 2022? It was in February, it was January 2022. Right here, right in this Gleisberg low. So what we see with these Gleisberg cycles is that they don't just last, I'm trying to move this other part here, there we go, is they don't have to last just 2 solar cycles. Here is very clearly 2, that this one's also quite weak there, solar cycle 7. You know, here it's almost like 5, but I'd say it's really these 3 that are that solar cycle low, that Gleisberg low. Right now, we're in the second one. We could have a 3rd solar cycle. Solar cycle 26 is no way to, it's not guaranteed to be strong. We may not even have a solar cycle 26. We could have a grand solar minimum. We don't know until it basically happens. There are forecasting signs that really adept solar physicists can look at, like termination events and a few other things, to forecast perhaps what's going to occur. But this is still such a new science that we could roll down into a grand solar minimum. And then as it relates to volcanic activity, we don't know what happens at that point. But there's signs that, again, when solar activity is low, like after all that loading, that's when this volcanic activity really surges. So we see that we are in this period of time and we're going into solar minimum. So every solar minimum in general, not just the Gleisberg 100-year-long cycles, but every solar minimum in general provokes more volcanic activity. And we just had this magnitude 8.8 strike Russia in 2025. So now we have the next few years. We've had all these other deep earthquakes and big earthquakes, multiple magnitude, high magnitude 7s, right? Kilauea is a great indicator that things are building, with it being the most active it's ever been. That's just one place, but Iceland, I've gone through the full list now for you, right? Things are really building up. Things are really building up. So again, no guarantee on anything, but I am forecasting that we have more volcanic activity coming in, and I think it could take some people by surprise. And the more earthquakes we get, the more likely that's going to really trigger this stuff. Because again, we clearly see that with this new data with the GNSS receivers, these GPS receivers, that these seismic waves, even after traveling through thousands of kilometers of the Earth, of the interior of the Earth, they're still able to measurably shift large regions. All of Japan shifted 6 millimeters. Now that's right after the fault was loosened by the magnitude 9.1. Still though, really, really profound, powerful things. So that is, I believe that is the update for you. Let me just make sure I have everything here. Oh, well, and just like one other example, I have a couple other things. Here's the uplift that occurred from the magnitude 7.7 in the Philippines. We see the before and we see the shoreline, then we see the after. That shoreline expanded by nearly 200 meters. So really incredible what can occur from a big earthquake. A huge expansion of the shoreline because we had this thrust up from depth. And we've also had some earthquakes in weird places. This is kind of the final thing to show you. I meant to mention this earlier. Check this out. Magnitude 6.1 here off the coast of Cuba. That's never been really seen before. That's the strongest earthquake in the Gulf on record. There's also aftershocks for that were less than magnitude 6. We've had 2 aftershocks now. But if we look at this, 26 kilometers down, this is oceanic crust. So that's at the bottom of the crust in the asthenosphere region. You're starting to interact with that mantle, basically. If we look here, we look at the moment tensor plot, and we check the rake, which is this third number there. It's positive, and it's close to 90, which means that it was basically a thrust up. So somehow, about 25 kilometers down, you had this thrusting motion up. Well, that's coming up from the mantle, baby. So there's weird things happening. It's not like we've never seen this before, but this is new. The magnitude 6.1 in the Gulf, we don't have that in our record until now. I'm sure it's happened before. I think the Earth is much more active in general than most people realize. We've had a big magnitude 7+ quake in this region here. I think in like 83, somewhere in that zone. We also had a big magnitude 7 quake in this region in the past. So these are way off of the plate boundaries and big fault systems, but you can get big high magnitude 7 quakes all across the board. We just had the magnitude 6.1 there. That was felt all across Florida. Mysterious sonic boom that was heard in South Carolina, in fact, across this entire region. No indication of what that was. We have no idea what that sonic boom was from. I reported on that for you guys live, as you remember, for those that watched. We don't know if that was from a meteor. We have no indication at all from our satellites, from eyewitness reports, nothing. Just a sudden, huge sonic boom reported to the USGS, and no seismic waveforms for that, like earthquake seismic waveforms. So we're seeing just across the entire Earth, there being more activity and energy coming up from the deeper parts of the Earth, from the mantle and from the asthenosphere, which seems to be indicating that the potential for really big activity is coming, or at least it's more likely, and probably be ready for that. And by being ready for that, I mean basically that just means make sure you have some food on hand, like dried beans, dried rice, dried vegetables, some dried fruit, things of that nature, and access like some sort of source of water. So that can be, if you have a natural spring nearby, that's great. Make sure you have some filtration for that somehow, but if it's a spring, you're probably good. Worst case scenario, make sure you have some energy generation, ideally probably solar, because generator, once you're out of gas, you're out of gas. Solar with a battery, you can do a lot with that. So these are all things that you can do to just in general be prepared, because certainly if you had been prepared in 1815, the year without summer, when there was famines everywhere and you had some stockpiles, however you did that, right? You've been much better off, because a lot of people starved to death because of that. And this El Nino, in general, super El Ninos are linked to droughts, disruptions, famines. We're in one of the worst crises as it relates to the growing season in North America, at least, since the Dust Bowl. You also have huge crop disruptions in Ukraine, the bedbasket of Europe, because of the war. So these systems are really under, they're fragile and increasingly coming under load. Let's call that. I don't want to say under attack, but in Ukraine, literally under attack, but coming under stress. They're stressed maybe to the breaking point. And these factors can just push it right over the edge. So really wild stuff happening right now. I will keep you up to date on everything and more. So thank you all for joining in today. Oh, I gotta go right now. So I'm sorry, I don't have time to respond to people's, well, there's not too many questions, but thank you all so much for watching. Wishing each and every single one of you well. Please take care of yourselves, and I'll see you all in the next video.